Okay, hello everybody to our MiDAS seminar for today. So today I'm very happy to host Professor Herodotos Herodotou from the Cyprus University of Technology. So Herodotos is working on things that are very interesting and relevant to some of the stuff that we're working also at this club. And today, I mean, he will talk about automatic distributed TH storage management in cluster computing, and we'll learn more about how to do data placement and how to think about different devices, which are very interesting questions. So before the Cyprus University of Technology, Herodotos took his PhD from Duke. He actually won. He was he had the honorable mention for the SIGMOD Jim Gray Dissertation Award, which is the most significant award for PhD thesis in our community. And he has spent a lot of time in industry, specifically Microsoft Research, Yahoo Labs, and Aster Data, and in other roles as well. We're really happy to have you here today, Herodotos, and learn more about your work. The floor is yours.
All right. Well, first of all, I want to thank you, Mano, for inviting me. It's an absolute pleasure to be here today. And thank you very much for that brief introduction. And since you already said everything that I was planning on saying, I think I'm going to go ahead and start with the technical presentation. You said today we're going to talk about automating distributed tiered storage management in cluster computing. And this is work that has been going on in my lab, the Data Intensive Computing Research Lab, for the past, I would say, 4 years. And most of the things that I'll present today are captured in a SIGMOD and a VLDB paper. All right, so let's put everyone on the same page. I have a long history of working on topics related to big data analytics, right? So nowadays, most big data analytical workloads are executed on a variety of platforms and a variety of systems that are either based on Hadoop MapReduce or Apache Spark. So these two big ecosystems out there are widely used. Now, all of these platforms typically process data that are stored on distributed file systems. The Hadoop distributed file system, or HDFS, is perhaps the most popular of the batch, but there are a few others out there as well. So over the last few years, there's been a few trends when it comes to this type of data processing systems. First of all, they all run on large clusters of commodity hardware. Now, this commodity hardware, these servers have seen a lot of improvements over the years. Their memory sizes keeps increasing. There are new types of memory devices that are out, like non-volatile memory, for example. A lot of these servers now host SSDs, in addition, of course, to hard drives and so on. Now, in addition, all this plethora of systems are now used to execute a diverse type of workloads, which of course lead to different types of I/O patterns for the underlying file system, right? So MapReduce workloads, for example, are typically batch-based, which means that throughput is their main concern. But you also have a lot of iterative workloads, like most machine learning workloads, for example, are like that. There's a big emphasis on real-time analytics and other types of interactive workloads where low latency is key. So those underlying, distributed file systems need to deal and work with all of these different types of I/O patterns. So a lot of these systems and some new systems have started trying to exploit these improvements in storage media. So there's a lot of file systems out there that have started storing data in memory and SSDs. Even HDFS, the last couple of years, have added support for storing data on other different storage media. The HDFS cache was also created for storing data in a cache, and so on. So when we set out to do this work, our goal was to design a new distributed multi-tiered file system, which we ended up calling Octopus FS, that is aware of the underlying storage media that have different capacities and different performance characteristics. Now, we wanted it to be distributed so it can run on clusters of commodity hardware and be compatible and play with all the big guys out there. we want it to be a multi-tiered file system, so we can actually exploit the fact that we have different storage media with different performance characteristics. We decided to stay at the level of file system because we wanted to maintain the file abstraction, which is the most general way of storing and accessing data. And then finally, we place a lot of emphasis on the performance characteristics of the storage media because we actually want to make decisions based on that. Now, designing such a file system, of course, has some key challenges involved. First, how do you actually design a system that's actually aware of this different media? And then how do you actually exploit or harness this storage media? Now, in order to address these different challenges and enable this awareness, we actually decided to focus on two principles that are sort of at odds with each other, right? So these are two principles which we call the controllability and automatability. On one hand, we wanted the file system that, of course, would automate as much of the process as possible, right? We don't want the user of the application to have to deal with low-level decisions. So automation is key. We need to have it. On the other hand, though, we still want to expose the different storage media that are available, to the outside world, to the higher-level applications, and give them control so that they can, for example, control the distribution and placement of replicas based on their own fault-tolerant and performance requirements, right? So these sort of two big design principles led us to a lot of the decisions that we made down the road, and I'll bring them out as we go along. So let's jump into the architecture of the file system itself. Now, this is clearly inspired by the HDFS architecture to a big extent. So we have a set of master nodes, which are responsible for handling the metadata of the file system, right? So you keep track of the directory namespace, right? So it's a file system. You have directories with subdirectories and files. Now, these files are typically broken down into larger blocks. HDFS, for example, breaks down blocks of 128 megabytes each nowadays, right? Now, these blocks are replicated and distributed across the different machines in the cluster. So, of course, the master also keeps track of the various block locations. Now, all the actual data are stored on the workers. Now, each worker has some locally attached storage media. It may have some memory available for the file system to use for storing blocks. We'll have some SSD devices, some hard drive devices. Maybe there's even a remote storage that's available. So now, if we look across the workers, we organize the storage media into storage tiers based on their I/O performance. So of course, there's the memory tier for all the data that are stored in memory. If we have SSDs available, we can have the SSD tier and so on. Now, it doesn't have to be memory, SSD, HDD tier. The system is flexible to accommodate different types of tiers, like I said, based on the I/O performance. So for example, if we have SAS drives and SATA drives in our cluster, these are two very different types of hard drives with different performance. We can organize them in two separate tiers. But at the end of the day, we have a set of tiers, of storage tiers for storing the different block replicas. So, as I said earlier, the files are broken down into blocks, and then those blocks are replicated and stored both across the different workers and across the different storage tiers. And this distribution can actually happen either based on client requests or automated policies. And we're going to get into that in a second. So the final component of the file system is the client. This is what the application or the users are using for connecting to the file system. So this client exposes all the typical file system APIs like create a directory or create a new file, open a file to read it, and so on. implementation-wise, we actually extended the Apache Commons file system API, which is what HDFS is also using. In addition, we exposed both the locations, I mean the workers, and the storage tiers of the block replicas. Now, the way we manage the replicas through the client is by introducing this new notion of what we call a replication vector. Now, a replication vector, it's a vector of numbers, where each number represents the number of replicas on a particular storage tier. Now, in the previous example, we saw a system that had 4 storage tiers: memory, SSD, hard drive, and remote. So our replication vector will actually have 5 entries in it. The first fold will represent the number of replicas we want on those 4 tiers. And we also have a 5th element, which we call the unspecified number of replicas. Now, I think this is the first time we're going to see how this, the 2 design objectives we have of controllability and automatability come into place here, right? So this replication vector can be specified when we create the file. So when a user or an application creates a file, they can use the replication vector to tell us exactly what they want. I want 1 replica of this file in memory, for example, and 2 replicas on hard drive. Right? So we give control to the application to tell us how they want the placement to take place. On the other extreme, maybe the application doesn't care. They don't want to deal with this. All they want is to create 3 replicas, and that's it. Now, this is where the unspecified entry comes into place. By using that, it's a way for the application to tell the system, you know what, I want 3 replicas, but I don't really care where you place them in terms of tiers. So the system gets to decide. So that's where the system should automatically decide what's the best locations in terms of tiers for these replicas. Now, in addition, we can also have, of course, anything in between. A user can come and say, hey, I would like 1 copy in memory for sure, and then 2 more copies, I don't really care. I'm going to let the system decide where to place it. Right? So there's a lot of flexibility given using this replication vector. And then finally, this unspecified entry here also enables us to be backwards compatible with HDFS. In HDFS, you only have 1 number. That's the replication factor. You get to specify how many copies you want. So in our system, that just gets translated into the number of unspecified tiers, and then Octabus FS gets to decide the tiers. Now, the other very powerful feature with the replication vectors is that we can use it through a single API and achieve an array of operations, right? By simply changing the replication vector, we can instruct the file system to create a new copy within the same tier, or maybe copy on a different tier, move it to a different tier, delete it from a tier, and so on. So by simply playing with this replication vector, we can achieve a lot of functionality. All right, now let's get into how the system actually works. And we're going to start with the data placement. A user or an application wants to create a file. Now, the process for creating a file is the following. The client will first contact the master and say, hey, I would like to create a file on this path. And they can also specify the replication vector, like we discussed. This is actually also optional. They might not specify anything, and then the system will decide the default number of replicas. Now, at the master, there's a very important decision that needs to take place. Where do I place these replicas? And this decision is actually made based on a pluggable data placement policy, and it's made for each block of the file. So for every block of a file that's getting created, this policy is invoked to decide where exactly to place the block replicas. So the master will then return a list of essentially worker tier pairs to the client, and then the client will connect to the workers. It will form a pipeline based on this list of workers that the master has decided, and we'll start writing the data in a synchronous manner. This is exactly the same way that HDFS works. All right, of course, the most interesting aspect of this problem is the decision. How do we decide how to make this placement? Our goal, of course, is to make good decisions, make a good placement. Now, what is good? How do we define good? We need to think about what kind of objectives do we have? What are we trying to achieve here? Okay, so let's think about this. We are a file system. We're thinking in terms of a file system. What are we trying to achieve? Well, there are actually a variety of things that we're trying to achieve at the same time. Number one requirement, of course, is fault tolerance. We want to avoid any data loss. If we lose a disk or if we lose a whole machine, we definitely don't want to lose our data. So that's definitely one key objective. Second, another very important objective is to maximize our throughput. We want to make sure that we can get really good performance out of our system. Now, if we think about it some more, there are other objectives that are really good in place. We have this array, of disks and different storage media across the different machines. We definitely want to balance our data. So we definitely want to distribute the data blocks across all these different storage media so that we can utilize them all. But perhaps even more importantly, we also would like to balance the load, right? So we also would like to distribute the I/O request across all of these storage media. So it's immediately obvious that we have different objectives that we would like to satisfy. And unfortunately, a lot of these objectives have different trade-offs or might even conflict with each other, right? So for example, we can easily maximize throughput. Sure, I'll just store all my replicas in memory. That's great. I'll get the best performance that I can. But then, fault tolerance will definitely suffer, right? Because I won't have any physical copy of my data. Or for example, maybe I'm going to try to always send my data on idle hard drives. Yeah, that's going to be good for my load balancing, but that's not going to be good for my data balancing objective, right? So what did we do? We have 4 different objectives. Some of them are conflicting. So we have set up this problem as a multi-objective optimization problem, right? So we have created a mathematical model to express each one of these objectives, and then set up the problem as follows. We would like to find the best R, number of replica locations, and I'm talking about worker key pairs, for storing a block that optimizes all 4 objectives simultaneously. In simple terms, we're trying to find a Pareto optimal solution for this optimization problem. Now, of course, this is a well-known problem, and there are solvers out there that are available for solving this type of problems. The issue here, and one of the big challenges, is that the decision space is actually combinatorial in nature. I mean, think about it. Think about how many different combinations there are for placing our replicas across different workers and across different storage tiers. So if we're to use one of these solvers, that would lead to an exponential running time. So to avoid this issue, we actually designed a greedy algorithm for finding a near optimal solution to this multi-objective optimization problem. Now, I won't go into the details of the greedy algorithm itself because there's a lot of other things that I would like to cover, but it's in the SIGMOD paper that we have. All right, so now we have a nice data placement policy. It's going to scatter our data across the workers and tiers. The next topic of interest is the data retrieval aspect. So an application or a user now comes in and wants to read this data. Now, the process for doing that is for the client to first connect to the master to find out where the different block replicas are located. So here we have a pluggable data retrieval policy who will decide where to read from. What's the best location to read from? And it will return back actually a sorted list of these locations, essentially instructing the client to go read from the best location possible. If that's not available, then it should go to the second best, and so on. Now, with regards to the data retrieval policy, our goal is to find the best replica location to read from, and we want to make this decision based on a lot of factors. There's the client location, where exactly is the client located on our cluster, which might even be outside the cluster. Where are the replicas located? What's our network topology like? Do we have multiple racks? How are they organized? What are the throughput rates of the different storage media in the network? And then finally, we also look into the active connections per worker and storage media to avoid, trying to read from a really, really busy server or disk. So we take all of this into account. Again, we create a mathematical model to represent all of this. And our data retrieval policy will then calculate the data transfer rate from each replica location to the client and return a sorted list of this location based on this calculation. All right, so now we have our file system. We have a good way to distribute the data across the workers, across the different storage tiers. We have good ways of reading from it. The next issue that we need to think about is that as time goes by, right, these different storage media are going to start to fill up. And of course, the smallest tiers, which are typically the most performant tiers like memory, will soon start to fill up. Therefore, we need to create some new redistribution policies that will decide how to move some of these replicas from higher tiers to storage tiers. Now, we call this process downgrade. Now, at the same time, as the workload is accessing all of these different data, some files might become very popular, they might become very significant, so they would benefit if we were to move them up the storage tier in order to get better performance. We call this process upgrade. Now, when we start thinking about this redistribution management, we'll realize that there are actually a lot of decision points here. There's a lot of decisions that we need to make, right? We need to decide when to upgrade or downgrade this file, which files to actually upgrade or downgrade, and then where in this hierarchy of tiers should we upgrade or downgrade the files to. So our key idea here was actually to track file access pattern and then utilize machine learnings to automate this type of decisions. Now, the idea of using data reaccess patterns was actually motivated by a lot of experimental analysis that were done on various workloads from Facebook, Cloudera, and Bing, showing that data reaccess patterns exist, right? Data are not just randomly accessed all the time. There are some data that are accessed periodically, for example, every hour or every day. Other data are getting accessed a lot now, they become very popular and then they sort of die out, and so on. Right? So the presence of patterns means that we can model them and try to make predictions. So we've set the problem as to use feature-based binary classification, right? So the idea is the following. If we can predict that a file will be accessed soon, then we should upgrade this file in a higher storage tier proactively in order to get better performance when it's going to be accessed. On the other hand, if we can predict that a file has become cold and will not be accessed for some time, then we can downgrade it to lower tiers and make room for new data to come in. So, inspired by some of the work that was done, especially in the caching area, which is sort of related to mainly to the downgrade process, we started thinking about what are the important file properties that can impact this type of decisions. Now, the three most important properties are recency, how recent was this file accessed, this frequency, how frequent this file has been accessed, and the file size. Now, all of these three properties are readily available, of course, in a file system. Now, if we think about, of course, the frequency by itself, that number doesn't really reveal the patterns. However, whenever a file is accessed, if we keep track of its the time that it was accessed, that is powerful enough to keep, to reveal some of the re-access patterns I would like to capture. All right, so the first step, of course, in any type of machine learning and binary classification is to convert our input data into feature vectors that we're going to use for training the model. All right, so let's think about what data we have. So we have, and let's focus for now on a single file. Let's say we have a file, we know its size, we know what time it was created, and we can also keep track of the different times that it has been accessed. Now, the way we generate features is the following. Timestamps by themselves are a horrible feature because it's a number that always keeps increasing. So of course we cannot use it as is. So the idea is to use differences between them, the time deltas essentially. So now to do this, we do the following. We introduce two data points in time, right? There's a point in time we call the reference point and a point in time we call the horizon. The idea of having a reference point here is to separate the perceived past from the future of a file access. So if we're here at the reference point, anything before it is the history of the file access. So here we can actually create, by using the different time deltas between the time accesses, the time between the reference point and the creation time, plus the last access time and the creation time, all of these time deltas plus the file size are used to create a feature vector, which we can then normalize and get a nice normalized feature vector. Now, the time period between the reference time and the horizon is what we call the class window, is the period of time we're interested in predicting whether a file has been accessed or not. Now, of course, now we're at the training data preparation stage. So this is the window of time that will tell us whether the file has been accessed or not. So if the file has been accessed during this time period, then our label will equal 1, right? We have an access. If the file was not accessed during the class window, then the class label will equal 0. Like I said, it's a binary classification. Was it accessed, yes or no? Now, the other very crucial thing to mention here is the following, right? So we can use this technique and we can, if we have a bunch of files, we can use it to generate a lot of, training data. The other interesting thing to note here is that if we simply slide the reference time, this reference point in time, if I move it here, now I create a new type of history. So I have a new feature vector and a new class window. So by sliding the reference time, I can actually create multiple training data and also see how it moves through time. Now, I'm going to take this idea a step further because everything that I've just discussed does not need to happen on historical data. We can actually do all of this in real time while the system is running, right? Think about it. The system is running. At any point in time, I can say, okay, freeze, this is current time, minus my class window, I get the reference point. Anything before that, I will use to generate my feature. This class window, I can look at the access to generate the label. So as the system is actually running, I can just simply generate new training data online. And it's very cheap to do because all I have to do is compute some time deltas. This is very basic, it's very minimal. I can do this essentially in nanoseconds. So as time goes by, I can periodically generate new online training data. This enables me to actually train my model incrementally. So this is not a one-time thing. I'm not going to just train the data once and then just have a model and use it. No, I can create a model, have it in memory, and then as time goes by, periodically generate new training data and update my model. This will make my model to adapt to any different changes in the access patterns of the files. So, and this is actually what we do. Now, at any point in time, if we decide that, hey, I want to make a prediction, what do? My current time now becomes the reference time, right? I'm here. This is my point in time. Anything before it is my history, and I can use it to generate my features like before. And then I can use the model to predict what's the class label for this class window. If it's 1, that means that the model predicts that the file is going to get accessed. If it's 0, the model predicts that the file will not be accessed. Now, since we have 2 major operations that we want to support, this downgrade and upgrade process that have sort of different requirements, we actually maintain 2 models. The only difference between the 2 models is this class window. For the upgrade model, we care if the file is going to get accessed soon. So we have a small class window for the model of the upgrade. For the downgrade model, we want to predict whether the file is going to get access or not for a much longer period of time. So for the downgrade model, we actually use a much larger class window, right? So in this way, we can train our model online, our 2 models online, and then at any point in time, we can use them to predict whether the file is going to get accessed or not. All right, so now this brings us to deciding what kind of model to use, right? So what are the key requirements here? We definitely would like a model that can be very accurate when we make predictions. We want to be able to predict whether the file is going to get access or not correctly. We plan to use this insight file system. So we want it to be really, really efficient, both in terms of CPU and memory. And then finally, we want a model that's adaptable. That's something that we can train incrementally as time goes by. For this reason, we selected to use XGBoost, which is a state-of-the-art gradient boosting tree algorithm. It's extremely efficient. It's amazing how efficient it is. It's actually been used the last few years quite a bit in machine learning competitions, actually in winning solutions of machine learning solutions, exactly because it has really good prediction accuracy and it's very, very efficient. We actually did consider and experimented with a few other alternatives. We started considering at first some, Bayesian approaches, like naive Bayes, but that assumes, feature conditional independence, which we don't have. I mean, we're trying to detect patterns over time. We played a little bit with the Bayesian belief networks, but that also requires some a priori knowledge, which we didn't want to just create some random assumptions about it. And then finally, we also implemented both SVM and artificial neural networks, but those were, much, much more costly, orders of magnitude costlier than XGBoost. And actually, in our settings, they didn't even really, give us really good accuracy to begin with. So all in all, XGBoost was a very good fit for our problem and gave us really, really good results. All right, now, so let's wrap the whole downgrade process, right? Because remember, we had 3 major decisions we needed to make. So this is the procedure, the downgrade procedure for downgrading from a tier. So let's follow this pseudocode. If a policy, so there's a pluggable policy that will make all of the decisions. If the policy says that I should start the downgrade process from this tier, then I should select the file to downgrade. Okay, I got the file. Then I need to select the downgrade tier. Where do I want to downgrade it to? All right, so now I'm going to schedule my downgrade. So this happens asynchronously. And then I have a do-while loop, essentially, that's going to repeat until the policy tells me to stop. So this essentially captures all the key decisions that we wanted to begin with. All right, so this process is actually called every time a block is added to a particular tier. A policy gets to decide when to start the downgrade so that we can do this practically, right? Unlike a caching system that waits until the cache is completely full to begin downgrade, Here, we want to be proactive. We don't want to wait until everything is completely full and then decide that we want to evict a block that's 128 megabytes in size. Right? We're talking about much larger sizes. So we need to be proactive and start earlier. Then the policy needs to decide, which file, and I'm going to discuss this in the next slide. Deciding where to downgrade to, we actually use a very similar formulation with the multi-objective optimization problem that I discussed earlier with the data placement. Because if we think about it, it's sort of a sub-problem of the placement policy. We just want to move a replica from one tier to another. So we reuse that functionality essentially here. And then finally, we have this condition that the policy can say, I want to keep doing this so that I can downgrade in batches. It's more efficient to schedule multiple downgrades to take place at the same time, and most likely they will take place at different workers in parallel. All right, so now with regards to downgrade, deciding which file to downgrade. Now, this in some ways the problem is similar to caching in cache eviction policies. And there are several out in the industry. We implemented over a dozen. I'm only going to talk about a few of them here. Of course, we implemented some of the most basic ones like least recently used or least frequently used, or a combination of the two. But we also implemented some other policies that were introduced in recent literature. There were two policies introduced at Pacman. This is a memory caching system that was presented in NSDI a few years back. It's a variation of the least frequently used policy that takes into account the file size and recency as well. We also implemented the EXD, the exponential decay policy that was proposed in big SQL. This is sort of like a hive equivalent system developed by IBM, presented at SOC a couple of years ago. That downgrades the file with the lowest weight, again, computes it based on recency and frequency. And then finally, we have our own XGBoost policy, which downgrades the file that has the lowest access probability in the distant future. Now, the upgrade process is fairly similar. There's a couple of minor differences from the downgrade process. So this upgrade procedure from a particular tier, and we might have a file in mind for upgrading. The steps are the same. If the policy decides that we should start this upgrade, then go ahead and select which file to upgrade. Then select which tier to upgrade to. Mark the file for upgrade, and then repeat this loop until the policy tells us to stop. So again, so this upgrade method is called either right after a file accessed, or it can also be called periodically, right? So say every, let's say, 10 minutes, I can call this method to see if I should upgrade something. Of course, in this case, I don't really have a file in mind. If I call this upgrade after a particular file access, then I know which file I'm talking about. So if the policy decides to start the upgrade, and I'll discuss this in the next slide, then select file to upgrade will simply select the file that triggered the starting process. Selecting the upgrade tier uses the same multi-objective optimization formulation that I discussed earlier. And the stop criteria is the following. If this access file was null, so I mean the periodic call, then the policy will decide whether there is more files that are worth upgrading or not. Otherwise, this will only happen once. All right, so for starting the upgrade policy, in a typical caching system, what happens when a particular piece of data gets accessed? It will typically always go through the cache, right? It will go through the cache. If it's not there, it will go to the underlying storage media, read it, and store it in the cache before returning it back. So the first policy we implemented does exactly that. On single, we call it the OSA policy, on single access. So if a file is accessed now and it's not already in memory. Yeah, we only use memory for this one. Then we're going to move it into memory. So this is a very simple policy. We also implemented this combination of least recently and frequently used to upgrade a file if its weight is higher than some threshold. Now, the big SQL system also proposed an upgrade policy for deciding when to move something into the cache of big SQL. So we implemented this policy as well. And then finally, we implemented our own XGBoost based policy, which will upgrade the files that have very high access probability coming up in the near future. All right, so let's move on to showing some key results. So all of our experiments took place on a local 12-node cluster. We had 1 master and 11 workers. The worker machines were set up with 3 storage tiers. Each worker machine had 24 gigs of RAM. 4 gigabytes of that is used for the memory tier of the file system. We also had an SSD drive and 3 hard drives. So we have 3 storage tiers for our file system. For our experiments, we used a variety of different benchmarks that are widely used, as well as some real-world workloads that we had access to. All right, so let's start with some micro benchmarks to begin with. The first results that I'm going to show is the average write throughput that the file system can achieve. For this, we use this micro benchmark, the DFS-IO benchmark, which will continuously create data on a distributed file system. And we measured the average write throughput. We tested 4 scenarios. One was the original HDFS that only uses hard drives. We tested HDFS with cache enabled. So in this scenario, each block is also placed into a cache, into a memory cache, and this is done asynchronously. And then we had our Octabus file system without the redistribution policies, and the Octabus file system with the XGBoost redistribution policies. So what do we see? Both in the HDFS case, with or without the cache, it doesn't matter for write, because writing to the memory is asynchronous. It's able to achieve around 80 to 90 megabytes per second. It's a stable performance as we keep writing, gigabytes and gigabytes of data. In the case of the Octabus file system, we see a decent improvement, I would say, in terms of average write throughput. We are around 130 to 140 megabytes for 2 reasons. First, we're also utilizing SSDs and memories to store this data. Of course, these are pipelines. That's why the difference is not that great. And then we also have all the fancy work that we do with our data placement policy that tries to also balance the workloads, balance the data around the different storage media, and all of that causes this improvement in the write through. Now you'll notice that I cut my graph in half. I'm only showing you half the story here, and this is because I wanted to first show you what happens as we start adding data to this file system. Now remember, this is a file system with 11 nodes, 4 gigabytes of memory each. So what happens at around 40-something gigabytes of data? Memory fills up. So we have no more memory to use for the file system anymore. So if we look at the rest of the graph, of course, that HDFS is not affected by that, so the performance stays the same. But the Octabus file system, without the redistribution policy, cannot use memory anymore. And that has as an effect for the write throughput to decrease. It's still a little better than HDFS because it's using the SSD drives as well, along with our multi-objective policy. But in the case of the Octabus file system with the redistribution policy, we see that the high write throughput performance remains the same because all data gets essentially evicted from memory as time goes by, allowing new data to come into memory. Now, what happens when we, with the retrieval aspect, right? So in the same benchmark also reads all this data that it was writing periodically. So in the case of the original HDFS file system, we're also getting around 150 megabytes per second of average read throughput per node. In the case of HDFS with cache, we see that we almost get double read throughput because now the cache is accessed a lot more. So that gives us a good boost on the average throughput. Of course, that only happens up until this 40-something spot, because after this point, the cache is full, no new data is placed there, so all the data from now on are read from disks. Now, if we look at Octavus file system, we see that we get almost a 4x improvement in the read throughput. We're getting around almost 550 megabytes per second of read throughput compared to 150. And again, at this inflection point, the Octavus file system, without the redistribution policy, stops reading a lot of the data from memory. So it only relies on SSDs and disk reads, which also give you some advantage at around 200 megabytes per second. But with the redistribution policy, the Octavus file system is able to maintain the high read throughput over 500 megabytes per second. So we can clearly see that essentially the data placement, the data retrieval, and the redistribution policies all have major positive effects on some raw performance metrics like the read and write throughput.
Herodotos, here, sorry, in the previous experiment, quick question.
Yes.
The reads and the writes happening at the same time? Like the reads of this graph and the writes of the previous graph are happening at the same time?
They're intermixed.
Intermixed. Okay.
So the way the workload works, it writes some data and then it reads it back. Then it writes some more data and then it reads it back. Yeah. All right. So now let's move on to see some more high-level evaluation. So what happens if we were to run some high-level workloads in Hadoop and Spark and replace HDFS with the Octavus file system? Now here we use the HiBench benchmark, which has a lot of applications implemented in both Hadoop and Spark. Now keep in mind that Octavus file system is backwards compatible with HDFS, so we didn't have to modify Hadoop or Spark or the applications. We simply replace the file system and everything worked. So what we did was we ran the HiBench benchmark over HDFS. Then we repeated all the experiments over Octavus file system, and here we show the normalized execution time. So we see that for Spark, the performance benefits we get are on average around 20%. Not very impressive, mainly because Spark was actually very well tuned and it was using a lot of its own memory, right? So the benefits of reducing I/O are not as high in Spark as compared to Hadoop. In the case of Hadoop, we can see that some of these applications have some major performance benefits, up to even 3 or almost 4x performance improvements by simply replacing the file system without making any other changes. So that we can see that in I/O intensive workloads, utilizing these different storage media, SSDs and memories, and memory in particular, can yield a lot of good actual performance improvements for high-level applications. Now, in the next set of experiments, we actually use some real-world production traces that we have from Facebook. These traces were collected over a 6-month period from a 600-node production cluster in Facebook. Now, based on these traces, we used Swim, which is a workload generation tool, to generate a representative trace containing 1,000 jobs that are scheduled for execution, following, of course, all the patterns of the original traces over a 6-hour period, creating and reading almost 1,400 of files and accessing a total of 92 gigabytes of data, which is more than double than the available memory that the file system has available. Now, in order to analyze our results based on the different jobs of the workloads, we actually we categorized the different workloads based on the data size. So we create 6 bins, 6 categories of jobs based on data size. We have some small jobs that only read a few hundreds of megabytes of data, and then we have larger jobs that read multiple gigabytes of data. And now here we also see some key properties of the workload. So the first thing to notice is that there's a heavy tail distribution, and this is well recorded in industry. The vast majority of jobs are actually small jobs that read a few hundreds of megabytes, whereas this monstrous job that reads tens of gigabytes of data are much smaller in number. However, if we look at the amount of cluster resources they utilize and the number of I/O that they generate, of course, this is almost reverse. Well, okay, maybe not reverse, but they're definitely more geared towards the big jobs. So big jobs will generate more I/O and they're more resource demanding in terms of the cluster. So in our first evaluation, we executed this workload using different policies. And these are both downgrades and upgrade policies together. So we executed this workload. We had HDFS in our first case, then we had Octabus file system without the redistribution policies. Then we had LRU as downgrade and the on single access upgrade. And then we had the LRFU, the EXD, and the Extreme Boost. We used the others, but I'm only going to talk about these ones in the presentation. The paper has a lot more results. In any case, so we executed the workload in all of these different scenarios and measured the completion time of all the different jobs. So what you see in this graph is actually the reduction in completion time over executing the workload using default HDFS. So the first thing to notice is that for small jobs, right, the performance improvement we're getting are not that high, which is sort of expected. I should, I guess, mention here that the small jobs here execute within seconds, whereas the bigger jobs take several minutes to execute. So if you have a job that completes in a few seconds, of the I/O component, it's only a small fraction of that. There's a lot of CPU overheads, scheduling overheads that take a big percentage of that. So of course, optimizing the I/O will not give you a lot of benefits in terms of completion time, right? So it used to run in 10 seconds, now it runs in 9.5 seconds. All right. But of course, as the jobs become bigger, the performance benefits that you can get increase quite a bit. Now, if we look at, if we compare the different policies with each other, we'll notice that some of the basic policies like the LRU or the LRFU perform pretty well for the smallest jobs, but then for the bigger jobs, they don't perform as well, which sort of makes sense because they don't really take the file size into account. They only care about recency and frequency. Now, the same actually happens with EXD. It's a policy that also doesn't take into account file size, and it actually performs very poorly for the big jobs. Surprisingly, it even performs more poorly than even the simplest of the basic policies. Excuse me. Now, if we were to focus, however, on the Extreme Boost policy, we'll see here that in all cases, we're getting the highest performance improvements in terms of completion time, and we're getting 20 to 27% of improvement, which in some cases is almost double compared to the second best policy. Now, looking at completion time is only half of the story, though. We also looked at the cluster efficiency, right? The amount of resources that the jobs use to do their work. So this job shows the improvements in efficiency over the default, again, HDFS file system. Now, the trends are very similar as we've seen before, right? So the bigger the jobs, the bigger the benefits, and XGBoost is doing better than everyone else. However, if we stop and think about this, we're actually getting double benefits here. Like if I were to focus on this line here, on the big job, this tells us that on average, these big jobs use 40% less resources, but and are able to complete. They have 27% faster, right? So we have double benefits. We use less cluster resources and we finish quicker, which means.
Can you just add a few more sentences to explain what do you really mean by less resources?
Yes, so cluster efficiency is defined as the amount of resources that the job consumes, and the way that is measured is the time that the individual tasks occupy the different machines. Right? Because all of these jobs are broken down into tasks that are executed in parallel. So if you sum up all the individual task times, that will tell you how much time the cluster was busy. It was involved in doing something.
Right. Yeah. Okay. Makes sense.
Mm-hmm. Good question. Yeah. All right. So next, some pure machine learning evaluation here to see how good our XGBoost model actually is. This graph shows the downgrade model evaluation. It shows the ROC curve, which essentially maps the true positive rate versus the false positive rate as we vary the threshold for our prediction. So if you don't know what AUC or ROC is, that's okay. What you need to keep in mind is that the closer we are at the 0-1 point, the better our evaluation is, our predictions are, both in terms of accuracy, precision, and recall. It's a very comprehensive measure. So the AUC, which is the area under this curve, we're able to achieve is 0.976, which is extremely high, showing that our model, the way we generate the features and the way we make our predictions gives us really good machine learning model performance in terms of getting high true positive rate and high false and low positive false positive rate. Now, this graph also shows some other things, but I won't go into those details. And then finally, we evaluated the incremental learning approach that we utilized, and we compared it against two other cases. The first case was the simple case where we run our workload for 1 hour, and then based on those file access patterns, we generate a model. And then we use that model. This is what we call the one-shot approach. Of course, we generate two models, one for downgrade and one for upgrade. And then this graph shows how the prediction accuracy varies as time goes by. So as we run the rest of the workload, what happens? So in this case, we trained the two models once. What we see is that as time goes by, their accuracy drops significantly, which means that after some time, these models are pretty worthless, essentially. They're not able to keep up with any changes in the workloads. They don't capture any new trends that may have appeared at time 2 or 3 or 4. Now, the other approach that we tried was to retrain our models every 1 hour. So every 1 hour, we retrain the model. The first hour, it's doing pretty good, very high accuracy. As time goes by, the accuracy drops. Here we retrain. The accuracy also, again, increases, and jumps up again because now this model has more information in it. So it has, modeled more patterns. as time goes by, it sort of drops again. We retrain, goes up and down, and we sort of see this trend continuing. But the model, in terms of accuracy, we see that it sort of varies between 80 and 90%, which is actually a pretty decent performance. However, when we look at the incremental learning approach, where the model is periodically updated, as time goes by, new training data comes in, our model gets updated, we see that our prediction accuracy for both models, the downgrade and the upgrade model, increases and sort of achieves a fairly constant rate of around, I think it's 96, 97%, so which is very good, very stable performance, showing that the model is able to learn new patterns, capture changes in the different patterns as they happen over time. Right, so with this in mind, we have developed this new file system right here, this Octopus file system that can run on distributed clusters. It's backwards compatible with HDFS, which means that it can be used by all of these different file systems, all of these different data processing platforms. Now, our story doesn't really end here because if we take into consideration the controllability aspects of Octopus FS and the fact that it exposes all this different information and it gives applications the power to control it, that opens up a lot of opportunities to do a lot of things up here, higher up the stack. For example, I'm just going to highlight a few. This gives us a chance to create a new task scheduler, both in MapReduce and Spark, that can schedule the tasks based both on the data locality, that is on which nodes the data is actually stored, but also on the storage tier. And this is actually something we did. We got some very good results. This work is actually under submission right now. So the graph that I showed you earlier with the Spark and that only 20% improvement, now that's gone. Now we get 2 and 3x performance improvement on Spark when we use our new storage tier aware Spark scheduler. We can also implement interesting prefetching algorithms because this scheduler, all of these schedulers, all of these systems have a scheduler. The scheduler has a queue of all the jobs and the tasks that are waiting. So they're essentially an oracle. They already know which data is going to get accessed soon. And we have enough, we give enough control, and there's an API available that application can tell us, hey, this data is going to get access soon. Let's move it up, right? So this is something we can do, and this is actually something we also implemented and experiment with in sort of at the same time while we also experimented with other workload scheduling algorithms. For example, especially in the case of MapReduce or even in cases of jobs that will do some work, will generate some intermediate data, and then another job is going to process that intermediate data. Again, a higher level system knows about this, so we can place this data on a higher level tier so that the next job can have it readily available. We can also cache hot data, or if we have an iterative workload, again, a machine learning workload, some of the data is accessed again and again during the iterations. Again, this is something that the application knows, so it can tell the file system. We've actually implemented all of this in a variety of different systems. One of them was Pegasus. It's a graph processing system. We got some very good results here as well. And again, we also have some thoughts on how we could sort of use this with other types of interactive applications by use some explicit memory management to pin working sets in cluster memory for other types of systems such as Impala, for example. All right, so all in all, I've presented the Octopus file system. It's a new distributed multi-tier file system that's actually aware of the underlying storage media and offers various features that aspire to both controllability and the automatability design goals that we've set from the beginning. We have policies that employ multi-objective optimization and lightweight gradient boosting trees for automating all sorts of data management decisions like data placement, data retrieval, and data redistributions. And then finally, everything was implemented in a real file system, and we have successfully evaluated over several benchmarks and real-world workload traces. Well, thank you once again for having me here and for your attention. And I'm now ready to take any questions.
Great. Okay, let's thank our speaker. So you feel free to unmute and thank our speaker.